Section 2.4, Systems of Linear Inequalities. In this section, our goals are to define a system of linear inequalities, represent the solutions of a system of linear inequalities in two variables graphically, and we'll see an application. So first, a system of linear inequalities is a set of two or more linear inequalities to be solved together. The graphical representation is the portion of the plane that satisfies all of the inequalities of the system. Now, when graphing these systems, we use the techniques that we've talked about in the previous sections, but we have to take into account all of the individual inequalities before we do any shading. All right, so let's see an example. We're asked to graph the solutions of 4x minus 3y is less than 12 and negative 3x minus 9y is greater than or equal to negative 9. All right, so I'll use colors to distinguish the two inequalities. All right, so the first inequality, we have 4x minus 3y is less than 12. I know I'm going to use a dashed line. And thinking of the equation, I'm going to use the intercept method. The x-intercept would be 3, 0. The y-intercept would be 0, negative 4. All right, so I'll plot those points and draw the dashed line through those points. I will test, I'll test 0, 0. Testing 0, 0, 4 times 0 minus 3 times 0, is this less than 12? Is 0 less than 12? Yes. So 0, 0 is a solution. But now I'm not going to do any shading yet. But what I am going to do is put some arrows saying that I would have shaded above that line. All right, so now let's look at the other inequality. Negative 3x minus 9y is greater than or equal to negative 9. I'm going to use a solid line. And let's do the intercepts again. The x-intercept, negative 3x equals negative 9. X would be 3, so 3, 0. And the y-intercept would be 0. Negative 9y equals negative 9y would equal 1. So we have 3, 0, and 0, 1. And again, now this time we use a solid line. Close enough. Again, I'm going to test 0, 0. Testing 0, 0 is negative 3 times 0 minus 9 times 0 greater than or equal to negative 9. Let's see, the left-hand side is 0. Is 0 greater than or equal to negative 9? Yes, it is. So 0, 0 is a solution of the inequality in orange, and so I would shade below that line. All right, so now I've taken into account each of the inequalities, but I actually only shade the region that satisfies both of these. So I need to be above the blue line and below the orange line, and so I would shade this region as such. So there's the region that satisfies both inequalities, and that's the graphical solution of the system. All right, here's another example. Graph the solutions of x plus y is greater than negative 1 and y minus 3 is greater than or equal to negative 5. All right, so I'll work in different colors again. We have x plus 2 is greater than negative 1. Wait a second, that only has one variable. Well, that's just x is greater than -3. So that's a dashed, and x is greater than -3, that's just a vertical line. All right, so where's x is -3? And we'll draw a dashed line there. Where is x greater than -3? Well, that would be to its right. So if this were an individual inequality, I would be shading to its right. All right, similarly now, let's work with the other inequality. Y minus 3 is greater than or equal to -5. Again, notice that's only one variable, only in terms of y. So adding 3 to both sides, y is greater than or equal to -2. We'll use a solid line here. And remember that y equals just a number is horizontal. So y equals -2 with a solid line. And y is greater than -2 above that line. So I'll use some little arrows to say I would have shaded above. So now, what satisfies all of the inequalities? This region to the right of the blue and above the orange satisfies both inequalities. So if I choose any of those points, it will satisfy both of those inequalities. All right, let's look at another example. 2x plus 3y is greater than 6, and y is less than or equal to -2/3 x minus 3. All right, so I'll work in blue for the first. 2x plus 3y is greater than 6. It's going to give me a dashed line. Let's see, my x-intercept would be 3, 0. My y-intercept would be 0, 2. 3, 0, and 0, 2 with a dashed line. Test 0, 0. So let's see, testing 0, 0 would give me 2 times 0 plus 3 times 0 is greater than 6. Is 0 greater than 6? That's false. So 0, 0 is not a solution, so I would shade above that blue line. All right, our second inequality. Y is less than or equal to -2/3 x minus 3. I'm going to use a solid line. I've got a y-intercept of 0, -3, and the slope is -2/3. So 0, -3, and the slope of -2/3. And I'll draw the solid line through those points. Let's see. Again, I can test the origin. Is 0 less than or equal to -2/3 of 0 minus 3? 0 is less than or equal to 0 minus 3 is -3. Is 0 less than -3? That's false. So if that were an individual inequality, I would shade below that orange line. So now, I'm only allowed to shade the region that satisfies both inequalities. Well, hey, these are parallel lines, aren't they? And I'm supposed to shade above the blue line and below the orange line. There's no point that will satisfy both inequalities. This system has no solutions. There is no region that satisfies both of these inequalities. So we can't shade anything, and in fact, these graphs are useless. Now, a system of inequalities doesn't have to have only two inequalities. We can have more than that. So here's an example where we have four inequalities, and we're asked to solve the system graphically and identify the vertices. The vertices are all of the points where the inequalities intersect and bound the region of solutions. All right, so let's see. Negative 3x minus 5y is less than or equal to negative 15. I'll work that one in blue. So let's see. I'm going to draw a solid line. Let's see, my x-intercept would be 5, 0. My y-intercept would be 0, 3. I don't have any scale here. Let's put a scale on here. Let's 2, 3, 4, 5, 6. All right, so 5, 0, 0, 3. Draw the line. Test a point. Let's test the origin. So let's see, negative 3 times 0 minus 5 times 0 is less than or equal to negative 15. Is 0 less than negative 15? That's false. All right, so for my blue inequality, I would be shading above. All right, in orange, y is less than or equal to 5x minus 5. Hey, that's in slope-intercept form. Again, I'll use a solid because of the or equal to. 5x minus 5. So the y-intercept is negative 5 and the slope is 5. All right, well, so let's see, I'd have a y-intercept of negative 5. That's down here somewhere. 3, 2, 3, 4. 1, 2, 3, 4. So we'd have 0, negative 5, and then the slope is 5, so let it rise. 1, 2, 3, 4, 5, and run 1. Let it rise. 2, 3, 4, 5, and run 1. So there's a couple of other points, and I'll use a solid line to mark the boundary. All right, test. Well, I can again test the origin. So let's see, testing the origin would give me 0 is less than or equal to 5 times 0 minus 5. 0 is less than or equal to negative 5, which is again false. So 0, 0 is not a solution, which means I would shade this side of the line. Okay, but we're not done yet. We have two other inequalities. We're also told that x is greater than 0 and y is greater than 0. Well, x equals 0 is the vertical axis right here. And x is greater than 0, well, that's to the right of it. Y equals 0 is the horizontal axis. And y is greater than 0 above it. So what that's telling us is we are working in the first quadrant. If we have x is greater than 0, y is greater than 0, we're working in the first quadrant. And we also need to now be above the blue line and below the orange line. So the region of solutions then is right here. This is the region that satisfies all of the inequalities. All right, so now we have that done. We're asked to identify the vertices. Well, two of them are easy. So what are the vertices? That's a vertex, that's a vertex, that's a vertex. Two of them are easy. The intersection of because they're on the horizontal axis, so the y value is 0, so we have what? This point is 1, 0, and this point is 5, 0. Not 5 times 0, but the ordered pair 5, 0. There's only one that's difficult, and that's this one right here. And that's the intersection of negative 3x minus 5y equals negative 15 and y equals 5x minus 5. Well, that's a system of equations. So now let's solve that system of equations. I'm going to erase my previous work here on the left. Alright, so we need to now solve the system negative 3x minus 5y equals negative 15 and y equals 5x minus 5. So I'm going to use substitution because I already have that 5x minus 5, y equals 5x minus 5, so I'll substitute that for y in the other equation. Negative 3x minus 5 by 5x minus 5 is negative 15. Negative 3x minus 25x plus 25 is negative 15. Negative 28x is negative 40. X is 40 over 28, which is dividing through by what, 4, would give me 10 over 7. Then y would equal 5 times 10 sevenths minus 5. So y would equal 50 sevenths minus 5. Now let's think ahead. 5 is the same as 35 sevenths. So then y would equal 15 sevenths. So the vertices are 1, 0, 5, 0, and 10 sevenths, 15 sevenths. Now it did say round answers to where needed to 2 decimal places, so we could round those. 10 sevenths is 1.43. 15 sevenths is 2.14. Alright, let's see an application. Harold runs a part-time handyman business in which he cleans pools and details cars. He charges $35 per hour for pool cleaning and $60 per hour for car detailing. Harold wants to make at least $345 per day, but can work no more than 8 hours per day. Let X denote the hours for pool cleaning and Y denote the hours for car detailing. Alright, so let's see. If we're going to let X denote the hours for pool cleaning and Y denote the hours for car detailing. Well, he can work no more than 8 hours per day. So then the hours pool cleaning plus the hours car detailing must be less than or equal to 8. He charges $35 per hour for pool cleaning, $60 per hour for car detailing, and wants to make at least $345 per day. So then 35x plus 60y, he wants to make at least $345, so greater than or equal to 345. Now also, we should note that the number of each of those numbers of hours has to be 0 or positive. So we will want to write x is greater than or equal to 0, y is greater than or equal to 0. Alright, so let's graph the solution to the system. Let's put some scale on these axes. 1, 2, 3, 4, there's 5, 6, 7, 8, 10. There's 5, 10. Alright, x plus y is less than or equal to 8. We could easily find the intercepts of that. Each of them are 8. So this is my x-axis, my y-axis. Alright, so we have 8, 0, and 0, 8. And I'll draw the solid line through those. The hours must add up to a number less than 8, so that's got to be below that blue line. Alright, 35x plus 60y is greater than or equal to 345. I'm going to try and use intercepts on that one. Let's see, 345 divided by 35 is 9.85. So let's see, we have 9, it's actually 9.86 comma 0. And 345 divided by 60 is 5.75. Alright, so let's plot those points. We have 9.86 comma 0, so that's about here. And we have 0, 5.75, so that's here. And we'll again draw a solid line through those points. Now, he wants to earn more than that amount. Right, so that solid line is exactly $345. He wants to earn more than $345, so should be shading above that orange line. Now, we also have the stipulation that x must be greater than or equal to 0 and y must be greater than or equal to 0, so that means we should only be shading in the first quadrant. All right, so we are shading to the right of the y-axis and above the x-axis. So then our region of solutions is this triangular piece right here. Above the orange, below the blue, and to the right of the y-axis above the x-axis. So, how many hours of cleaning pools and detailing cars can he work to make a minimum of $345 per day? So if he wants to make exactly the minimum, he would be somewhere on that orange line. So let's suppose he works 2 hours on one job. So let's say he worked 2 hours on the on X, so 2 hours for pool cleaning. So if X equals 2, then 35 times 2 plus 60 times Y, let's let that equal 345. So then 70 plus 60Y is 345. And so then 60Y is equal to 275. Let's see, 275 divided by 60 is 4.6. So, he can work 2 hours cleaning pools and 4.6 hours detailing cars, and earn the minimum of $345. All right, find the vertices and state their meaning in the context of the problem. Again, two of the vertices are fairly simple. We have the first vertex over here, 0, 5.75. So let's see. He can work, if he works only 5.75 hours detailing cars, he will earn at least $345. Also, though, he can work, if he goes to 0.8, he can work 8 hours detailing cars and earn at least $345, without going over the other requirement that he only wants to work 8 hours per day. Now, what about that other vertex? So that other vertex, let's solve the system x plus y equals 8 and 35x plus 60y is equal to 345. I'm going to make a substitution here. I'm going to say that y is negative x plus 8. So then 35x plus 60 times negative x plus 8 is 345. So then 35x minus 60x plus 480 is 345. So then negative 25x equals, let's see, 345 minus 480 is negative 135. And dividing through, we have 135 divided by 25 is 5.4. Now, if x is 5.4, then y would equal negative 5.4 plus 8. Y would equal 2.6. So, we have 5.4, 2.6. So, if he works 5.4 hours cleaning pools and 2.6 hours detailing cars, he will work exactly 8 hours and earn exactly $345. All right, and graph the solutions of y plus 2x is greater than negative 5 and y is less than or equal to x plus 3 using the graphing calculator. All right, so in the previous section we talked about how to use the graphing calculator to graph inequalities. So notice that the first inequality, y plus 2x is greater than or equal to negative 5. I want to rewrite that as y is greater than or equal to negative 2x minus 5. And the second inequality I can leave alone, y is less than or equal to x plus 3. Let me bring up my calculator. All right, my y1 is negative 2x minus 5. Now I move over to the left, and I want to get a greater than. So remember, the greater than is the upper triangle, the upper shaded triangle. It looks like that. My y2 is x plus 3. And remember, we want a less than here, so that's the lower shaded triangle. It looks like that. I'll hit the graph key. Now, it shades both. So it doesn't understand that we have a system of inequalities. Now, if you're going to reproduce this, what we need to remember is we really only shade the region that satisfies both. So let me drag this over and up and amend it a little bit. So what I would want you to do is, maybe do a brief reconstruction of this graph, and we would certainly have solid lines. But I would want you to only shade this region that I'm shading in blue. All right, so that's how we need to understand the graphing calculator. All right, that concludes the presentation for section 2.4.